Hello, I'm Giuseppe Vecchio, and today I will present StableMaterials, enhancing diversity in material generation via semi-supervised learning. Authoring materials for 3D scenes is one of the painful bottlenecks in computer graphics. Specialized skills, loss of time, and the result still depends on whatever asset you happen to have. Learning-based methods have helped, but they all hit the same wall. PBR datasets are tiny compared to image datasets. That gap shows up directly in what this model can generate. Existing material generation models fall into two groups. The first generates SVBRDF maps directly, trained only on annotated PBR data. Physically correct, but diversity is limited to the available datasets. The second type uses large image models to first generate a texture, then runs an SVBRDF estimation on top. You get diversity, but you inherit all the biases of inverse rendering. The model has to guess specular, metallic, and height from one shaded image. We wanted to get the best of both: physical correctness from supervised training and diversity from large-scale image priors. With StableMaterials, we wanted to be able to leverage large-scale annotated data to generate directly high-resolution SVBRDF maps that should be tileable, and ideally, we want all of that to be fast. To do so, we propose a semi-supervised training strategy and use a two-stages generation to achieve high resolution, plus feature rolling for tileable generation. We leverage consistency models to have a 4 steps generation. Diving deeper into the method, StableMaterials is a latent diffusion model that can generate all 5 PBR maps directly: base color, normal, height, roughness, and metallicity. The trick is in how we train. We use SDXL as a teacher, but we can distill it in the usual way, because SDXL produces single shaded images and we produce material stacks. The domains don't match, so we built a shared latent space. We first train a VAE to compress material maps, and then fine-tune variants to compress single texture into the same latent representation. Then we run 2 losses in parallel. The supervised loss handles annotated PBR materials in the usual diffusion way: noise prediction against ground truth. The adversarial loss takes unannotated textures generated by SDXL, runs them through our model, and the latent discriminator pushes those denoise latents to look like real material latents. On top of the base model, we distill a latent consistency model that brings inference down to 4 steps per stage. That's where the next problem shows up. Noise rolling needs many steps to converge. Our fix is features rolling. Instead of rolling the noise input, we shift the feature maps inside every convolution and attention layer of the unit. This preserves edge continuity throughout the network itself, rather than relying on the iterative averaging across diffusion steps. We compare against MathFuse, MathGen, Material Palette, and Adobe Substance 3D Sampler on both image and text prompting. StableMaterial beats or matches all of them on clip score and clip IQA. To conclude, you can take a domain-specific generator with a tiny dataset and meaningfully scale its diversity by distilling from a large image model, as long as you build a shared latent space and let supervision carry the physical plausibility.